Hey everyone, we're looking at chapter 12 here and static equilibrium. So we want to see what it takes for an object to be in static equilibrium. Like in this crane picture here, they can see that that crane is lifting a very large weight and the crane is not tipping, it is not moving. So if it is not tipping and moving, then there must be something to balance it on one side or the other. And that's really what we mean by the term equilibrium. All things should be equal. And what are those things? Well, we saw them in lab today. The conditions for static equilibrium is there is no motion. That means no linear acceleration and no angular acceleration. They both must be zero, which means that all our forces are going to cancel out and the object must remain at rest, and all our torques must cancel out, so the object will not angularly accelerate. The nice thing about when we do sum of forces equals zero or sum of torques equals zero is that for the torques, we can pick where we want our pivot point. And you'll see how powerful that'll be in a few seconds here. So really just two rules for statics: no forces and no torques. Everything's got to cancel to zero. Seems kind of easy, right? So we had to talk about this concept we saw in class about the center of gravity. Our calculating net torques, we need to assume that gravity is acting at one single point. And so the weight of a bar or the weight of a ladder or the weight of anything needs to be considered when we are looking at forces and how far they are from our pivots. An easy way to find the center of gravity we showed you was to just move your fingers until you get to that point where the object balances. You get no rotation, so that means that all gravity is acting at that one central location. You can check out this video from Veritasium here where he's also showing you how to find the center of gravity of objects fairly quickly. So here's a mobile. This mobile is perfectly in static equilibrium. Every weight is perfectly balanced, and we could draw out all the forces on each of those. But what we started off today in the lab was with seesaws, and that a seesaw is really just two objects trying to torque the bar in their favor and torque it in their direction. The big bear is torquing it in one way and the little bear is trying to torque it in the opposite direction. We showed what we needed to do to make the seesaw balanced in terms of making torques equal and opposite. So let's do an example here for a bridge. For a bridge, as cars move from one side to the other here, the forces will change as the car moves based on where that mass is located along the bridge. In the demonstration, you can see that our setup is this plank of wood, and that plank of wood has two scales, one at one end and one at the other end. And if you would look carefully at those two scales, they actually read about the same amount, around 1,600 grams, which means that the whole board is around 3,200 grams. So that whole board is getting its entire weight distributed among each of the two pillars there. So what am I going to do in the demonstration here? Well, in the demonstration, I have a car that I'm going to place on the middle of the track. And when I place it on the middle of the track, both scales change. They actually both change identically because the car is evenly at the center of gravity of the entire bar. That means both pillars are just distributing the weight equally. But watch what happens when I start moving across the bar. So as I bring that car towards the left pillar, you can see that the force is changing in the left pillar. The force has gone up, and in the right pillar, the force has gone down. As the car starts to drift from one side to the next, watch each pillar. Each pillar is now pushing less or more depending on where that mass is located. So the forces change as we go across that beam. So let's show mathematically how you would set up a problem for solving for net torques. Okay, so here's our setup here. We've got the two pillars, we've got the bridge deck, and we've got a car sitting on the bridge deck. So what we want to do is figure out how much force is each pillar providing and each pillar pushing. So let's first identify the forces. Well, if I look down the bar, I would say that the first force is the car. So the car has a force of gravity pointing straight down. And let's give that value. We'll say that this force of gravity is 2,500 newtons. So as we look at this scenario, what else has physical weight? And what else has weight is the actual bar itself. At the center of gravity, gravity is trying to pull the entire bridge deck straight down. And let's give that a value. Let's say that the force of gravity on that is 30,000 newtons. So it's much heavier than the car. All right, well, if we go back to rule number one says all our forces must equal 0. That means that all our up forces and our down forces must cancel out, and all our right forces and our left forces must cancel out. So I see 2 down forces, that means there must be 2 right forces. So my 2 right forces must be the left pillar and the right pillar. So I can see that those forces are pointing upwards to hold the bridge deck up. The question is, how strong are each pillar? So we want to know the force in the left and the force in the right. So let's set up how we would do this. Well, we want to sum the forces. So summing the forces and making sure that all the forces add up to 0, we can say that 0 must equal the force in the left pillar plus the force in the right pillar minus the force of gravity of the car minus the force of gravity of the deck. So there is my force formula. If I want to figure out which ones I have already, I know the weight of the car and I know the weight of the bridge deck. Things I don't know are the forces in the left and right pillar. So forces aren't going to help me, then I'm going to have to go to my second equation. My second equation says let's look at torques. So let's set this up. I'm going to need my net torques to sum to 0. So that means there's got to be a torque from the left pillar, a torque from the right pillar, a torque from the car, and a torque from the deck. So I've got 4 torques along the bar here. What I want to do is make sure that all my torques add up to 0. But the nice thing about torques is that we can pick our pivot point. So I'm going to go back to here, and I'm going to make my pivot point right here. I'm going to make that pivot point the right pillar. So if I pivot everything off of that, then I can say that, all right, the middle of the deck is half the length of the deck, and let's say the whole deck is 10 meters, so it's 5 meters away. The car is 3 meters from the left pillar, or 7 meters from the right pillar, and the left pillar is the full 10 meter length all the way down. So let's put in our torques for every single force. And what we want to focus on is direction too. If you look at the weight of the bridge and do your R cross F, your thumb points out of the page. Do it for the car. Do R 7 meters cross 2,500 meters. You'll get that force pointing out of the page. Do the same thing for the left pillar. Do R cross F. This time the force is up, so it's now into the page. So when we have our 3 torques here, the blue torques are all trying to make this thing spin in the anti-clockwise direction, while the left pillar is trying to make the whole thing spin in the clockwise direction. So let's look at summing those torques. The torque in the right pillar is actually 0, since there is no distance. But the left pillar is the force in the left pillar multiplied by 10 meters, and that is a negative torque, trying to make the thing spin clockwise. The car and the deck are doing positive torques. They're trying to spin it counterclockwise. So that means I need the force of the car times 7 meters, and I need the force of the bridge deck times 5 meters. So if I set this up and I look to see what I'm solving for, the things I have again is I have the weight of the car and the weight of the deck, and I have their distances now. So go ahead and solve for the force in the left pillar. What you should get is that the force in the left pillar is 16,750. So of that 32,500 newtons of force down, the force in the left pillar is taking 16,750 newtons of that total force. So if I know the left force, I come back here and now I've got 3 things out of my 4 forces. Solve for the right force, and if you solve for the right force, you should get 15,750 newtons. So the left pillar is pushing up harder than the right pillar. And that makes sense because there's more weight shifted towards that left pillar than the right pillar. But as the car starts to drift from one side to the other, the right pillar is going to take on more and more weight as the left pillar gets to back off a little bit and not support as much as it used to. So this is happening constantly as you drive across a bridge. The one pillar feels that full force when you're right on top of it, but as you drive away, it loses some of that upward force, and the other pillar eventually pushes up harder to compensate for all the extra weight. So this should help you in the challenges that we put out for tonight's homework. Try to do challenge 1 and 2 off of the balanced lab worksheet, and we'll see if we can get those predictions right tomorrow. One thing that we can check on this to make sure we know what's happening, if I do take away the left pillar, which would be a terrible thing if you were driving, but if the left pillar would suddenly disappear, so would that torque. And if you look at it now, the only things acting on the bridge are the car and the bridge deck. So the car and the bridge deck wouldn't just fall straight down, they would actually rotate and fall in the counterclockwise direction as they collapse. So you can see that the torques are positive and the direction that they want to move is positive based off of that pivot point on the right pillar. I could have picked the left pillar as my pivot point and you would have got the same answer as well. Try it for yourself if you don't believe me.